We start. Okay. Okay. The last day of lectures. Thank you. So today it's going to be about particle acceleration finally. And we'll work it out. So particle acceleration in a specific setup, the one of a non-relativistic shock wave, which is the mechanism that's usually invoked in astrophysical accelerators to explain particle acceleration. And we'll see why and why its properties are so suitable to explain possibly what we observe in cosmic rays. So let me start. The original idea dates back to 1939, and it is by Enrico Fermi. And Enrico Fermi initially thought of his acceleration mechanism as due to interactions between particles and magnetic perturbations. When he thought of magnetic perturbation, he was actually not thinking of, the kind of wave-particle interactions that we've been considering so far. At least what he had in mind is that there could be regions in the universe in which magnetic perturbations were especially strong, in particular magnetized clouds, okay, high magnetic field clouds. We do have magnetized clouds that move with some speed v in the galaxy, let's say, and a particle, a relativistic particle, in this version that I'll tell you in the first part of the lecture, we're already dealing with particles that are relativistic. So energy much larger than mass energy. And so a particle can meet a magnetized cloud, enter the cloud. Within the cloud, scattering with magnetic perturbation is especially effective, so that particles' velocities are isotropized within the cloud, and then the particle will finally exit the cloud with some energy to be quantified. So the initial energy of the particle, we'll call it E1 at its entrance in the cloud. Let's call mu the angle, the initial angle between the particle direction of motion and the direction of motion of the cloud. And let's call mu prime the particle between the final direction of motion of the cloud when it gets back to the uniform ISM and the speed of the cloud. Okay, for the bunch of people who've just arrived, we're now doing first order Fermi, well, we're now doing Fermi acceleration. This is actually going to turn out to be a second order process. But so the idea of Fermi was that particle could interact with magnetized moving clouds. The cloud moves with respect to the unperturbed ISM, in which we do know that particles are to a very high degree of approximation isotropic. Okay, we showed that particle isotropize in the ISM thanks to scattering with magnetic perturbation. Then they occasionally, okay, no, it's fine. At least there are people coming, I'm happy. Okay, so the idea is that this blob here is a magnetized cloud, okay, that's moving with respect to the ISM, the system in which particles are initially isotropized by general magnetic perturbation. The cloud is moving with a velocity v in some direction. A particle can occasionally encounter the cloud, get into the cloud, and in the cloud, it undergoes the elastic scattering with magnetic perturbations that we've learned to know. And it finally exits with some different direction, mu prime, with respect to this is the angle between the particle velocity v and the velocity of the cloud, capital V, okay? And the first task of the day is going to be to compute E2 as a function of E1. Now, what happens to the cloud? So as soon as it enters what happens to the particle? The particle enters the cloud with an energy E1, and since the cloud is moving with a velocity v, the energy in the cloud system E1 prime is going to read what? Gamma E1 minus C P1 mu, minus beta, sorry, P1 mu C. Okay, this is just the Lorentz transformation, and gamma is just the cloud Lorentz factor. So gamma is equal 1 square root of 1 minus beta squared, and beta is the ratio between the cloud velocity and the speed of light. Okay? Okay, sorry, yes, let me try to write bigger. So E1 prime is equal gamma E1 minus beta C P1 mu. Okay? Right. So P1 mu is the projected momentum of the particle along the cloud direction of motion. This is just the Lorentz transformation, right? So the parallel component to the change of reference frame counts. No, it's going to be non-relativistic, whereas the particle is going to be relativistic. So let me keep that gamma, but that gamma is of order 1. The reason I'm keeping is that I already know that this is going to be a second order process, so I need terms of beta squared. So I need it in this computation because I know the end result, that the 0th order vanishes. Okay. So this is the E1 prime, and okay, so this is the particle energy in the cloud system as soon as it enters the cloud system. Then the particle energy E21, so right before exiting the cloud, the particle will have an energy E2 prime equal to E1 prime, right? Because we said that it only undergoes elastic scattering, which again means that all the magnetic perturbations it interacts with are low phase velocity magnetic perturbation. The phase velocity of these hydromagnetic waves is of order VA over C, with VA the Alfvén speed, and the Alfvén speed we showed is much, much smaller in typical diffuse astrophysical setups than the speed of light. Okay, then my actual question was, what is E2, right? The energy of the particle when it leaves the cloud. So E2 is going to be gamma E2 prime plus, this time, beta C P2 prime mu prime. Right? Yeah, here there is a prime. I don't know if you can see it. So I call the exit angle mu prime. Okay. Now, first of all, so since we're dealing with relativistic particle, CP1 is just E1, right? And CP2 prime is just E2. Prime. Okay? So now let me try to express E2 in terms of E1 straight. I can write that E2 is equal gamma E2 prime 1 plus beta mu prime. This is just a rewriting of this expression. Then I use the fact that E2 prime is equal E1 prime. Okay, let me write it, otherwise it's going to be too fast. E1 prime 1 plus beta mu prime. And then I further express E1 prime in terms of E1. which means that this is going to be gamma squared E1 times 1 minus beta mu times 1 plus beta mu prime, right? Okay, now what I am actually after is the gain of or loss of energy in the interaction between the particle and the cloud. So what I'm going to compute is the delta E over E, which is equal to E2 minus E1 divided E1. Okay? What is this going to be? So this is going to be gamma squared E1, 1 minus beta mu, times 1 plus beta mu prime minus E1 divided by E1. So I can write delta E divided by E equal to, of course, E1 disappears, and I have an expression for gamma, which gives me 1 minus beta mu times 1 plus beta mu prime minus 1 minus beta squared, gamma squared. Okay? What is this? Gamma squared now can effectively be approximated as 1, but I am left with 1 minus beta mu plus beta mu prime minus beta squared mu prime minus 1 plus beta squared. Okay, 1 goes away, and finally delta E over E is equal to beta squared minus beta mu plus beta mu prime minus beta squared mu prime. Okay, now this is an equation that we want to keep, not to rewrite it all the time. And this is the energy gain or loss by a single particle in an encounter. What we want to compute is the average of this energy change, fractional energy change, average over what? Over entrance and exit angles, right? So over mu and mu prime. So we want to average this on the probability for the particle to enter the cloud with some mu and exit the cloud with some mu prime. So we want to learn what the P mu entrance probability with a given angle mu is and what P mu prime in exit is. So let's call it P1 and P2. What do you expect them to be? Well, the probability for a particle to enter the cloud with some angle mu is going to be P1 of mu proportional to what? To the relative velocity between the particle and the cloud. Now, since the particles are isotropic in the reference frame of the ISM out of the cloud, this is going to be v, velocity of the particles, minus capital V mu. Okay? Of course, since this is a probability, you want its integral to be 1, which means that you want integral between minus 1 and 1 in the mu of v minus v mu times some constant a, normalization constant, equal to 1. This implies that 1 is equal to v mu minus v mu squared divided by 2, computed between minus 1 and 1, times a, sorry. So this implies that a is going to be what? So this is v, the integral of mu between 1 and minus 1 is 2v, whereas if you compute mu squared between minus 1 and 1, this is 0. So the normalization constant is a equal to v. And we can finally write that p1 of mu is equal v minus capital V mu divided to v. The small v is actually going to be c in the end, right? We are dealing with relativistic particles, I stated from the very beginning. Okay, let's compute now P2. In the cloud, particles are isotropized again. So the probability of exiting the cloud with some angle mu prime is going to be uniform, just uniform, right? So P2 mu prime is going to be some constant b. What is this constant b? The one that guarantees the probability to normalize to 1. So b times integral between minus 1 and 1. So let me clear this. I can clear this, right? So integral d mu b is just equal to b, which implies that b is equal 1/2. Okay? So P2 mu prime is just going to be 1/2. Okay? Equipped with these two probabilities, now we go and compute, let me use this blackboard. Now we go and compute the average of delta E over E, which is going to be the integral between minus 1 and 1 d mu prime P2 of mu prime times the integral between minus 1 and 1 d mu P1 of mu of the energy change, of the fractional energy change, which is then beta squared minus beta mu plus beta mu prime minus beta squared mu prime. Okay, good morning. Yeah. No, it's not the magnetic field, it's the normalization constant. Let me call it, so P0. So this is the normalization constant of the probability, exit probability. Oops, something bad happened. A chair broke. Yeah, this happens all the time. I mean, I was surprised that in all these days, no chair had broken. So good, we're done. Okay. Okay. Okay, so let's compute this. This is equal to, so let me change the two integrals, minus 1 d mu, and let me use the right probabilities. So I can put 1 over 4v in front of everything. okay? And then I use the expressions for the probability. So this is V minus capital V mu, okay? Which, let me leave it like this right now. And then integral between -1 and 1 in d mu prime, okay, of this thing here. Beta squared minus beta mu plus beta mu prime minus beta squared mu prime. Okay, so this is 1 over 4v, and then let's compute the first integral, which is sort of straightforward, v minus v mu. Okay, the first integral is just beta squared mu minus beta mu squared divided by 2. No, sorry, I'm integrating in mu prime. Sorry, beta squared mu prime minus beta mu prime plus beta mu prime squared halves minus beta squared mu prime squared half. Okay, between -1 and 1. And of course, the terms that contain mu squared just vanish, mu prime squared just vanish. So I'm left with 1 over 4v integral between -1 and 1 d mu of v minus, now I can approximate it just because it's simpler. V is of order C, okay? So let me get rid of this V here, and I will write 1 minus beta mu, okay? Times beta squared, and this is the term in mu prime, which gives me a factor of 2 integrated between 1 and -1, minus 2 beta mu. Okay? So let's continue on this blackboard. I'm trying to write big, but it's this means many, many blackboards. Okay, so now I have 1/2 integration between -1 and 1 in d mu, 1 minus beta mu, sorry, 1 minus, let me do the, let me do the product. Let me compute the product. So that is beta squared minus beta mu, and then minus beta cubed mu, and plus beta squared mu squared. Okay? And this reads 1/2, and then I have beta squared mu minus beta mu squared halves minus beta cubed mu squared halves plus beta squared mu cubed thirds between -1 and 1. First thing to notice, there are no terms that are linear in beta. This is second order effect in V over C. Okay? So this is the reason why this is called second order Fermi acceleration. Because there are, right now there is still one term in beta, but this goes to 0 as soon as we develop the integration. Okay, so the final result is 1/2, and then I have 2 beta squared. This is 0, this is 0, so 2 beta squared plus 2/3 beta squared, right? Which is 4/3 beta squared. Okay? So what have we learned? That in this case here, let me go back to the previous blackboard and let me get rid of the stuff that's now become useless. In this case here, where the probabilities are P1 mu and P2 mu, average delta E over E is equal 4/3 beta squared. So I'm left with a second order. So the change of energy of the particle is slow because it's very small at each particle encounter. And this is due to the fact that, in fact, there is no, that the probability for the particle of tail-off encounters with respect, so the particle will gain energy in head-on encounters. So it enters with mu and it goes back in the same mid-plane, right? In that case, the particle will have a net energy gain. In the cases in which the particle enters the cloud and then exits in the same direction of entrance, in the same, with sort of the same projection, and with projection in the same mid-plane of entrance, the particle will just lose energy. Okay, so the fact that there is a net energy gain has to do with a slightly larger probability due to the relative velocity v minus capital V mu, with a slightly higher probability of tail-off, of head-on encounters rather than tail-off encounters. Okay. Okay. Now, of course, so as I said, this is a slow mechanism. There is a much more efficient version of this mechanism, as if you can make all the encounters between the particles and the magnetic perturbations isotropizing them all head-on. Is this possible? Yes, it is possible in an astrophysical setup if you have a shock wave. Okay. Now I must tell you a bit about shock waves. Who is familiar with them? 2, 3, 4 people. Okay. Okay, so let's hope you don't find it too boring. So basic hydrodynamics of an astrophysical shock wave. How do we, what is a shock wave, first of all? So usually when you have a fluid, any kind of fluid, including plasmas, when you have a fluid, the presence of an obstacle in the fluid flow is told to the fluid by sound waves. Okay, there is an obstacle. This means that there is some density perturbation. I have like something denser in the middle of the flow of the fluid. The fluid much ahead of the obstacle is told by the presence of the obstacle by sound waves. And usually what happens is that the fluid can adjust and move around the obstacle, okay? So if it is informed soon enough, it can go around the obstacle. But if the obstacle is moving with respect to the fluid at a speed that's larger than the speed of sound, there's no way to tell the fluid well ahead of the obstacle of its presence. And then what happens is that there is no time to divert and go through the obstacle somehow to adjust to the presence of the obstacle, and you have an impact between the flow and the obstacle that leads to a density increase, okay, to a very large, well, in principle, large density increase. You end up with a pile up of the fluids in front of the obstacle. Now, in astrophysics, shock waves, the present, well, let's say fluid motions that are supersonic, that are at speeds larger than the speed of sound, are actually extremely frequent in a number of setups. First of all, explosions, like supernova explosions. These eject matter at a speed that is much higher than the sound speed in the ISM. And I mean, you can easily see it. So usually you have a kinetic energy of a supernova explosion, which is of order 10 to the 51 erg, okay? And this is in terms of this is kinetic energy, so this is 1 mass of the ejecta in the supernova explosion times V ejecta squared. And if you go and compute this equal to ESN, sorry, let me call this ESN, with a mass of the ejecta, which is typically between 1 and 10 solar masses, you immediately find that the velocity of the ejecta when it starts, when the supernova starts to propagate, is of order several thousand kilometers per second, okay? Between 5 and 10 times 10 to the 3 kilometers per second. To be compared with the sound speed in the interstellar medium, which is of order 10 kilometers per second, okay? So you usually have the conditions for the formation of a shock wave. If, as usual, if things are not clear, just tell me. M ejecta is of order 1, 10 m sun, with m sun, with which I'm not sure you're familiar, being 2 times 10 to the 33 grams. Okay? Okay, so how do we write the equations to, for the shock system, for the shocked fluid? Can I get rid of this? Yes. So the fluid dynamics is usually governed by conservation equations that conserve the following 3 quantities: mass of the fluid, momentum of the fluid, and energy of the fluid. And these are written as conservation equations. So in the form, the density, so let me call rho the density of the fluid. The rho dt is equal, and I'll write it directly one-dimensional, okay? We're going to deal only with one-dimensional systems, but all conservation equations are in the form of a time derivative plus the divergence of a flux, okay? Now I'm just writing it 1D, but this is a divergence in 3D, okay? This is conservation of mass. Yeah, let me. Sorry, okay. So conservation of momentum is this is conservation of momentum, and finally conservation of energy. So energy is kinetic energy plus internal energy, okay? And P is the fluid pressure. Sorry, I didn't say, okay? So conservation of mass, momentum, and total energy. Now, let's assume, so we will have a frame that is like this. So this is the shock. This is upstream of the shock, the unperturbed fluid. Let's refer to this as 1, region 1, the unperturbed fluid. And region 2 will be the downstream, the fluid that has learned about the presence of the obstacle. What must change between upstream and downstream is essentially the sound speed, right? Because as I was telling you, what is the idea behind this? That if I'm moving too fast, I don't know what I have in front, and the sound speed is not enough of informing me of the presence of this fast-moving obstacle. What the shock transition will do is to increase the temperature eventually of the fluid so that the sound speed, which is essentially the temperature, so let me, yeah. I guess you all know what sound speed is. Sound speed is Cs squared. The square of the sound speed is dP, d rho in a fluid. Now, usually we use the adiabatic condition, which means that P is proportional to rho to the minus gamma. And, sorry, to the gamma. P is proportional to rho to the gamma. And so Cs squared is just equal gamma P over rho, which is essentially gamma temperature of the fluid, okay? So what the shock transition will actually have to result in is an increase in the fluid temperature, okay? So that the sound speed becomes large enough that then the fluid is informed, can readjust to the presence of this obstacle. Does this make sense? Okay. Okay, so now let us consider steady state, which means that we get rid of these terms here. And let's, how do I do this? Okay, I'll use this blackboard. Let me see. Yes, I can clear this. So now let's compute the jump. So we have a shock, which means that this change is going to be discontinuous. In the shock frame, I can get rid of the time dependence. I'm assuming that everything is stationary in the shock frame, and I will write the conservation of mass, momentum, and energy on the two sides of the shock, which implies that ρ2 U2, the shock is an infinitely thin discontinuity in this frame, and so ρ2 U2 downstream of the shock is going to be equal ρ1 U1. I'm basically integrating that equation across an infinitely thin discontinuity, okay? So this is the first equation, then I have ρ2 U2 squared plus P2 equal ρ1 U1 squared plus P1. And then I have U2 ρ2 U2 squared divided by 2, and then I have this epsilon here, which is the internal energy of the fluid, which I can relate to the pressure once I know the adiabatic index, because epsilon is equal to P divided gamma minus 1 with gamma, the fluid adiabatic index. Okay? So epsilon plus P is going to be equal gamma minus 1 plus 1 divided gamma minus 1 P. So gamma P divided gamma minus 1. Okay? So here I can write rho 2 U2 divided by 2 plus gamma minus 1 P2 equal U1 rho 1 U1 squared divided by 2 plus gamma divided gamma minus 1 P1. Okay? Now, let me introduce two quantities. The first one is the compression ratio R equal U1 divided by U2 equal rho 2 divided by rho 1. Okay? The second equality I get from the first equation. Once I define R as U1 divided by U2, based on the mass continuity, this is also equal to rho 2 divided rho 1, which is why I call it compression ratio. It's the ratio of the densities downstream and upstream of the shock. Then let me also define another quantity, which is the shock Mach number. M is the ratio between U1 and the speed of sound. So in principle, this trick of integrating the continuity equation, the continuity equations across an infinitely thin layer, I can play in any part of the shock, in any part of the fluid, if I'm in a steady state, right? I've just got to read a reading of the time dependence, and I'm integrated on an infinitely thin layer. I can do it everywhere. So if this Mach number is actually, so if U1 is less than the speed of sound, so M less than 1, I expect that to just lead to continuity of everything, and we will verify it. I expect things to become interesting when M is large. If the velocity of the fluid upstream, which you can call the velocity of this the relative velocity between the fluid and the obstacle, is larger than the speed of sound. Okay? Now, another thing that I want you to notice is that P1, okay, so let's go on with this equation. So I can here divide by U2, and then let me divide the equation 2 and 3 by rho 1 U1 squared, okay? So I can write rho 2 U2 squared divided rho 1 U1 squared. You immediately see that this becomes just the ratio between U2 and U1 based on equation 1, right? Well, I'll do it with step by step. 1 plus P1 divided rho 1 U1 squared, okay? I'm just dividing equation 2 by rho 1 U1 squared. So this is 2, and this is 3, and 1. Okay. Now let's take a look at this bit here. So P1 divided rho 1 U1 squared, I can write it as 1 over gamma CS1 squared, okay, speed of sound in the, CS1 squared divided by gamma, okay, speed of sound in the medium upstream of the shock divided by gamma, divided U1 squared, okay? And this is 1 over gamma M1 squared. So I've expressed the ratio between the pressure and the momentum flux upstream of the shock in terms of the Mach number. Okay? So the larger the Mach number, now you understand The smaller the ratio between the pressure and the energy density in the kinetic energy density in the flow. Okay, I can now use that expression and equation 1 into this equation 2 to obtain 2c, so this was 2b. 2c is going to be what? 1 over r, this is what's left of the first term, plus P2 divided by rho 1 U1 squared equal 1 plus 1 over gamma M1 squared. Okay? And this, and okay, let's leave it like that. Let's work now on equation 3, and we'll do the same. We will divide by rho 1 U1 squared half, well, rho 1 U1 squared. So now we've learned how it works, so I can directly write 3b equal U2 over U1, which is 1 over R, plus I multiply everything by 2, 2 gamma minus 1 P2 over rho 1 U1 squared equal R times 1 plus 2 gamma minus 1, and I again express this as 1 over gamma M1 squared. Again, I've only used the equation of continuity and the expression for P1 over rho U1 squared in terms of the shock-Mach number. Okay? Now I can use an expression, what I get here from P2 rho U1 squared, which is just this minus 1 over R. Okay? Do you allow me this step? Okay? No, because rewriting all the time is a bit, you know, takes a lot of time. And I can input this expression in this equation here. So I now have 1 over R plus 2 gamma divided gamma minus 1. Then I have plus 2 gamma minus 1 M1 squared. Okay. Where I simplified the gammas. Minus 2 gamma minus 1 over R. Okay. And this is equal to R1 plus 2 gamma, 2 gamma minus 1 M1 squared. Okay. Let me move to this blackboard now. And now we need to solve that equation to find what? To find R as a function of M1. How do we do it? It looks complicated, but it's not that bad, because I can notice the following things. So first two terms left and right, I can write as 1 over R squared minus 1. I've just divided everything by this R. So let me divide here by R. Okay? So 1 over R squared minus 1. Then I have plus 2 gamma minus 1. That's divided by r, whereas the same term there is divided by r squared. So this is 1r, 1 over r minus 1. Let me check the sign. So it's a minus, right? So this is this term here and this term here. Okay? And then for the third term, that is what? Plus 2 gamma minus 1 m1 squared. And this is 1 over r minus 1. Okay? I group the terms in a smart way so that I see that 1 over r minus 1 appears everywhere. Because then I can use the double product and write this as 1 over r plus 1, 1 over r minus 1, and I can get rid of 1 over r minus 1 everywhere, right? So one of the two solutions, this is a second quadratic equation in R. One of the two solutions is the straightforward solution R equal 1. The other solution is what? 1 over R plus 1 minus 2 gamma, gamma minus 1, 1 over R, plus 2 gamma minus 1, m1 squared equals 0. Okay? So let's, can I clear all this? Because yeah, okay. Okay, now let's solve for R. So I have that 1 over R multiplies 1 minus 2 gamma, gamma minus 1, right? And this is plus 1 plus 2 gamma minus 1 and 1 squared equals 0. Okay, so now I can compute this, and this comes out to be gamma minus 1 minus 2 gamma, which is equal to minus gamma minus 1. So I can write here 1 over r, gamma plus 1, gamma minus 1, equal, I had a minus in front, so this is equal to 1 plus 2 gamma minus 1 and 1 squared. Okay? Does it work? This gives you minus gamma divided minus gamma plus 1 divided gamma minus 1, so this is what I just wrote. Okay? So finally, I have an expression for R. So R is going to be equal to gamma plus 1 divided gamma minus 1, 1 over 1 plus 2 gamma minus 1 and 1 squared. Okay? From here to here. Did I do something wrong? Check on me, please. What is this? Then I'll give you the break, I promise. We're almost there. So what is this equation telling you? So first of all, let's check the different limits. Are we all there? Everything is okay? Okay. So let's check what happens as a function of, so first of all, gamma. What is gamma? Well, for a non-relativistic fluid, which is what we're dealing with, gamma is equal 5/3. Okay? Now, let's see, however, what happens in the two limits, m1 that tends to infinity and m1 that tends to 1. So m1 that tends to infinity is easy to do, right? R becomes just gamma plus 1 divided gamma minus 1. This is m that tends to infinity. Okay? On the other hand, if m1 is equal to 1, r is equal to gamma plus 1, gamma minus 1, 1 over 1 plus, gamma minus 1 plus 2, gamma minus 1. Okay, m that tends to 1. And this is what? This is just 1. For m1 that tends to 1, there is no discontinuity. There is no supersonic motion because m is just the ratio between the speed of the fluid and the speed of sound. So if in the absence of supersonic motion, there is only one solution. The compression ratio is equal to 1. It's just continuity. Both solutions of the compression ratios are equal to 1. On the other hand, if m1 becomes large, if the motion is highly supersonic, the compression ratio tends to a number that only depends on the adiabatic index of the fluid. And for a non-relativistic plasma, that R, you can easily see to just equal to 4. Okay? Okay. Now, let's take a break, and 5 minutes break. And after the break, we'll discuss how the dynamical quantity change across the shock transition, the density, the velocity, the pressure, and then we'll add how the magnetic field hopefully present, because otherwise no, the particles just do not interact with anything, because we're dealing with collisionless particles. So, and we will also see how the magnetic field changes across the shock. And then we'll work out what happens to particles encountering this shock as compared to encountering the cloud. Okay, so 5 minutes break. Okay, now let's see. Now we've learned about the jump in density and in velocity. So basically that R equal 4 means that the velocity downstream of the shock, U2, is 1/4 of the velocity upstream. So this was U2 and this is U1. And so we've learned that U2 is equal U1 divided by R, so divided by 4 for this standard setup. Let's see what happens to pressure and magnetic field. I think I can clear it all. Okay, so first of all, so U2 divided U1 is equal 1/4. Rho2 divided Rho1 is equal 4, right? Continue with the equation. Now let's see what happens to Rho2 U2 squared divided Rho1 U1 squared. Well, this is easy, right? This is 1/4. Okay? Which means that while initially all the fluid energy was in the form of kinetic energy, and you see it from here, the ratio between the fluid pressure and internal energy divided Rho1 U1 squared was much less than 1, tending to 0. Now, what's left in kinetic energy is just 1/4 of what it was. And the rest must have gone into pressure, right? So P2 divided Rho1 U1 squared, which was our total energy, is what? for m that tends to infinity is just 1 minus 1 over r, which is equal to r minus 1 divided by r, so 3/4. So what the shock has done to the fluid was to convert kinetic energy into thermal energy, increase the speed of sound. That was the purpose, and it reached it. Next question to answer is, what happens to a magnetic field that might be there in front of the shock? So there must be also, if we want to scatter particles, if we want to interact with our cosmic rays, the shock must have a magnetic field, which will also change across the shock discontinuity. And how will it change? Well, according to Maxwell's equation. So basically, divergence of B equal to 0 is telling you that the component of the magnetic field normal to the shock must be conserved. You integrate dB dx, dB parallel dx across the shock, and of course you obtain that B2 parallel is equal to B1 parallel. Right? This is just divergence of B equal to 0 integrated as we did before across the shock. How about the perpendicular component? Well, we also know that in steady state, curl of U cross B, which is the electric field in astrophysical setups, is equal to 0. Okay? Remember, we said that since the plasmas are such good conductors, the electric field is equal to U cross B, because the total force, electric plus Lorentz form on the plasma, wants to be 0. So the plasma adjusts in such a way that the electric field is equal to, well, U over C in reality, cross B value. Okay? Now, if I compute curl of U cross B, and again I integrate along the shock, this is giving me d by dx, that's the shock velocity, U B per. Okay? So this is U parallel and this is B per. Yes, U parallel and B per. Parallel and perpendicular is always with respect to the normal to the shock surface, so to fluid propagation direction. Okay, so what does this imply? That B2 per U2 is equal B1 per U1, and ultimately that B2 per is equal to U1 over U2 and hence R, B1 per. Okay? So if I have, as we often assume, a completely tangled magnetic field, we'll discuss this at the very end of this lecture, hopefully, why we could expect a completely tangled magnetic field in front of a shock, which is the case if it is the particles, the accelerated particles generating most of the field in front of the shock. So we will have that B2, which is equal to square root of B2 parallel squared plus B2 per squared is also equal to square root of B1 parallel squared plus R squared B1 per squared. Okay, I used the two equations, the two boxed equations into here. Okay, but for a tangled field, it will also hold, this is going to be small. For a tangled field, we will also have that B1 parallel squared is just 1/3 of B1 squared, and B1 per squared is 2/3 of V1 squared, right? Okay, so let me input this information here, and I find that this is B1 per 1/3 plus R squared times 2/3 B1. Okay? It's just that the perpendicular components are 2 and parallel is 1. Okay? So I get to this equation, and where do I write it finally? Let me sacrifice the pressure. So in the end, if you compute this for R equal 4, you see that this is 16, right? Times 2 is 32, plus 1 is 33, divided by 3 is 11. So V2 is typically square root of 11 V1. Okay? This is the typical kind of compression that we expect for the magnetic field with a shock if the field upstream of the shock is tangled. In the downstream, we'll have a larger magnetic field, larger by a factor square root of 11. Okay, let's keep this information. Why is this important? Well, first of all, if you compress the magnetic field at the shock, in terms of radiation, and the main process that tells you about the conditions of non-thermal particles in the shock is radiation, leptonic radiation, synchrotron radiation, that knows about the magnetic field. And the fact that the field is larger in the downstream immediately tells you that you will mostly learn about non-thermal particles in the shock from synchrotron radiation in the downstream. Okay? So it is important to connect that theoretically to the downstream, to the upstream, to understand what's going on in the upstream, which we'll see is especially important in terms of setting the maximum energy that you can achieve at a shock. Okay. So far so good. We've learned what the shock does to a fluid, but why are we interested in what the shock does to a fluid? Because now we're going to show, well, this is immediate to see actually, that the shock is an ideal system for the Fermi mechanism to work. Because in the case of a shock, if particles cross and recross the shock, at each single crossing, they will experience a head-on collision with the fluid. Tail-off collisions are not there anymore, which were the ones that were, making the energy gains low in the case of the cloud. Why is that? So let's now look at the shock from the point of view of an upstream particle. So here, the thing is like this. You had an upstream velocity U1. In the shock frame, you have an upstream velocity U1 and a lower downstream velocity U2. Particles are approaching the shock. The fluid is approaching the shock from the left with a speed U1 and is leaving the shock to the right with a lower speed U2. But now, if I'm in the upstream, how does the shock look like? Well, in the upstream frame, you'll see the shock that's moving towards you with a speed U1, right? And the downstream fluid that's moving towards you with a speed which is U2 minus U1, right? So the speed is U1 minus U2, but it's towards you. Okay, so in the upstream, I see the downstream that's moving towards me with a speed U1 minus U2. What happens in the downstream? Now I'm sitting in the downstream and looking at the upstream medium. Now in the downstream, the shock is moving towards me with a speed U2, And the fluid upstream is moving towards me with a speed u1 minus u2 in my direction. So in the downstream, okay? So what does it mean? That every time I cross the shock, from whatever side, upstream or downstream, I always see the fluid on the other side of the shock moving towards me. So this is all head-on collisions, right? Every time the particle crosses this boundary, it sees the fluid moving towards it, no matter in which direction it crosses. Okay, so what, in all that we discussed at the beginning of last hour, where does this enter? It enters in the probabilities. This kind of physics must reflect in the expression in terms of mu and mu prime of the probabilities of going from one side to the other. Okay, the exercise is exactly the same as for the cloud, but with different probability distributions. In the case of the cloud, we had in the case of the cloud, these were the probabilities. What are the probabilities now? The energy change is exactly the same. So the idea is the particle crosses the shock and then gets isotropic by perturbation in the downstream medium or in the upstream medium, I don't care. What I do care is the probability of entering with some angle mu and leaving with some other angle mu prime. Now, let's consider a particle that from the upstream goes towards the shock. What is the probability of this condition? Well, now I have only half of the plane, right? So the only particles that have a probability to cross the shock from upstream to downstream are the ones whose pitch angle, pitch angle I used with respect to the magnetic field, now it's with respect to the flow velocity, whose pitch angle with respect to the flow velocity is between 0 and 1, right, from the upstream. The upstream is on the left. So mu must be between 0 and 1 for the particle to cross the boundary. So P1 of mu is going to be proportional to mu, the particle inclination with respect to the flow velocity, with some constant A, let's call it P0, so that we don't make any confusion with vector potentials as it was before with B. Normalized to 1, I have integral now between 0 and 1, P0 mu in the mu equal to 1, which means P0 mu squared half between 0 and 1 equal to 1, which implies P0 equal to 2. Okay? So the probability P1 mu is just going to be mu divided by 2. 2 mu. Does it make sense? No. You're puzzled. I've just assumed, I just said that the probability of crossing is proportional to the angle, and that the only particles that can actually cross the shock are from upstream to downstream are the one with a positive direction of the velocity in the right midplane, so between 0 and 1. Same holds true for the crossing now back from the downstream to the upstream, but now P2 of mu is going to be finite only, of P2 of mu prime, only for mu prime between -1 and 0, between 0 and -1, right? And so again, what I will find with exactly the same reasoning is 2 mu prime in this change between the probabilities here and the probabilities here for the cloud is all basically the physics of the different efficiency of the two systems at accelerating particles. Let's compute now the energy change at such a shock. Okay? So, again, delta E divided by E is going to be equal to the integral between -1 and 0. Let me put the 4 in front of everything. D mu prime, integral between 0 and 1, d mu, and delta E, I left it there. So it's beta squared minus beta mu plus beta mu prime minus beta squared mu prime. The delta E over E is just the same, right? It's only the probabilities that change. So this is what? 4 integral between -1 and 0 d mu prime. And now let's compute this integral here. So that is beta squared mu squared half minus beta mu cubed thirds plus beta mu prime mu squared half minus beta squared mu prime mu cubed thirds between 0 and 1 equal 4 integration between -1 and 0 d mu prime, and here I have, so beta squared divided by 2 minus beta divided by 3 plus beta mu prime divided by 2 minus beta squared mu prime divided by 3. Okay, next step, next integration. This is equal to 4, and then I have beta squared halves mu prime squared halves minus beta divided by 3 mu prime squared divided by 2, plus beta mu prime cubed divided by 6 minus beta squared mu prime cubed divided by 9. And this is between now -1 and 0. Let me go ahead and, let's we will remember that the magnetic field, we will remember these jumps without further stress. So okay. So now I have that delta E over E average is equal to 4, and now let's compute it. So this is in 0 is 0, so there is a minus, beta squared divided by 4, okay? The same is true, it keeps the sign, so it becomes a plus the beta over 6, so plus beta over 6. Hopefully I did it correctly. Here the minus goes away because this is a cubed term, so it becomes plus beta over 6. Okay, yeah, it should be right. Okay, minus beta squared, and this again cancels the sign, minus minus, so it stays a minus beta squared divided by 9. Okay, so finally delta E over E, and you immediately see that now we have first order terms left, is equal to what? So this is 4 times 2 divided by 6, so 4/3 beta. We have a first order term left, minus, and that is 13 over 36 beta squared. Okay? So, what has changed? Well, now the average gain of the particles is first order in beta. The first order term stays there if you compare it with that 4/3 beta squared. So the gain is much faster. Is of order V over CE. So the particle gains energy much, much faster. Notice the appearance of this term here, which is negative, but you see that it will never overcome beta because it's in terms of beta squared. So the gain will always be positive and will be first order V over C. And we won. This is the fastest you can get in terms of energizing particles through collisions with a fluid. Now, I would like to stress that this seems a trick in a sense, right? Why with a particle, I mean, you have a collision between a particle, collision. This is collisionless particles. They do not experience actual body collisions. So what is actually making their inertialization? What is making the work of the particle? We said that magnetic fields alone cannot energize particles, so there must be some electric field in this case. And of course there is an electric field, because as soon as you've introduced either a velocity gradient, the cloud moving with respect to the medium in which you were isotropized, or the shock, so two fluids moving with respect to one another, you've introduced in the system an undeletable electric field. The electric field is there, there is no way the plasma can compensate it as soon as there is a sharp change of velocity. Okay, so it's the electric field that the shock that's doing the work, and we'll discuss in a while, well, next hour, how you interpret this in terms of the transport equation that we worked out 2 days ago. Okay, so we've learned what the energy gain for the particle is in the system. Now we want to understand what kind of particle distribution we can expect in energy. What kind of particle spectrum we find. If you have doubts, just stop me. Oh, no, you're right. This is not 36. You're right. This is 9. Yes. Thank you. No, I don't remember the second order term, so I wasn't checking. Yeah, you're right. That's 13 nines. Yes. Okay, so let's see what happens in terms of particle spectrum. I can now clear all this. Okay. So, okay. Yeah, it's like 5-10 minutes, but we started late. Is it okay if we go ahead? Just, it's like 5, yeah. It's almost time to break, but I'll still like 5 or 10 minutes. Okay, so in order to work out the particle spectrum, what kind of information do we need? Well, we've learned that there is an energy change in each crossing, which is 4 beta divided by 3. Oh, by the way, in the case of the shock, what is this beta? This is the velocity of the fluid relative to the particle. So beta in the shock setup is, as we discussed earlier, u1 minus u2 divided by c. Right? Is the velocity with which the fluid comes towards you. Okay. So let's say that delta E over E equal 4/3 u1 minus u2 divided by c, and let's just call it G gain right now. Once I defined that G, I can write that after K crossing of the shock, the particle will have an energy which is what? At crossing K plus 1, the energy will be G times 1 plus, sorry. So the energy will be Ek plus G Ek. Correct? So this means that this is going to be 1 plus G Ek, which, if I want to relate it to the energy at the beginning of the shock crossing, becomes 1 plus G to the K E0. Okay? Now, how many particles will cross the shock K times? Well, this depends on the probability that particles actually escape the system. Where can they escape the system? From downstream or from upstream? In the upstream, the fluid is moving towards the shock. So if you wait for infinite time, the shock will catch up with anything that's in the upstream. Okay? The downstream instead is moving away from the shock. So from the downstream, you can actually use particles. They can get far away from the shock and never be caught again by the shock. Right? So I must worry about how many particles leave the shock from downstream as soon as they are downstream. So I must, because the number of particles and K after that will do K cycle is going to be 1 minus P escape and, sorry, let's K plus 1, 2, and K, which is going to be 1 minus P escape to the kappa and 0. Okay? Let's try to understand what this P escape is. To do this, I must compute the flux of particles that leaves the system forever in the downstream. So the downstream is on the right, as usual. Sorry, I cleared the shock. This is up and this is down. And the shock is moving like this. Okay? So the flux of particles that will flow to the right, that will flow forever to the right in the downstream, what is it? How can I compute it? I can compute it assuming, and this is an important bit of physics, that particles are isotropic in the downstream frame. I'm assuming instantaneous isotropization. So this number of particles is going to be all the particles that in the downstream have u2 plus their velocity mu, their projected velocity along the x-axis. The one escaping will have this larger than 0. They will fly to the right. Right? So the probability of leaving the system is what? So the condition for them to leave the system is mu larger than minus u2 over v. So the probability of leaving the system is therefore all the particles that are moving with mu between minus 2 over v and 1. Correct? I mean, does this make sense? The particles are isotropic. Their distribution, that F2, let's call it, in the downstream does not depend on mu, and the probability is proportional to mu. How many particles are we talking about? Well, this is F2, mu squared halves computed between minus u2 over v and 1. No, sorry. No, yeah, I wrote the wrong thing. I need to write, it's a flux, so here I have u2 plus v mu, okay? This is the flux of particles that are leaving. So I need to input the velocity with which they're leaving the shock, which is u2 plus v mu. Okay. So this is now F2. And now I have u2 mu plus v mu squared halves computed between minus u2 over v and 1. And this is equal to F2. And so I have u2 plus v minus, and then there is an extra minus, so plus u2 squared divided by v, and then I have a minus that stays minus u2 squared v divided by 2. Okay? Which I rewrite as F2 twice actually, F2, which multiplies. So this is 2u2 v, let me also multiply it all by v, 2u2v plus 2v squared plus u2 squared, 2 times u2 squared, minus u2, no, I think I forgot a 2 here. Yes. I forgot a 2 here. No. Where did I forget a 2? I'm sure I forgot a 2. Here I forgot a 2. Right? Because this was u2v halves. Right? But when I performed this integration, I think I forgot to write a 2 down here. So this is now 2u2. Here is a v squared. This is 2u2 squared minus, I did something weird. V squared plus, no. Oh, okay, yes, this was u2 squared divided by v minus, and this was u2 squared, okay, Yes, this should be correct. So this is 2u2v plus v squared plus u2 squared times 2 minus u2 squared times v. Okay.
Shouldn't be.
Yeah, what did I do? Where did I go wrong?
Maybe the last term shouldn't be, because we have u squared multiplied by another u's.
Here.
So maybe a u cube or...
No. So this was the integral, right? Now I compute it in, this is correct. Right?
Yeah,
then I compute it in 1, and this gives me u2.
Yeah. Yeah, the last time it is cube, right?
No, u2 must be squared. And because this was minus u2 over v squared, and then I have a v here. So it becomes a v. Ah, that's right. Sorry. Okay, yes. Okay, thank you very much. Yeah. Okay. Okay, so this is minus u2 squared. Right, thank you very much. Yeah, I mean, even in terms of dimensions, it was completely wrong, so thank you, yes. Okay, so at this point, these two terms just go to give me 2, no, so, and this 2, of course, goes downstairs. I was, yeah, okay. Now, we're making it slowly. So, F2 divided to V times U2 squared plus V squared plus 2U2V, which is just U2 plus V squared divided to V. Okay? So we'll learn that V, the flux phi of escaping particles, is just, and then there is F2 multiplying everything, is just F2 divided 2V U2 plus V squared. Okay? Now, the escape probability, however, is going to be P escape equal to the ratio of the flux of particles that escape divided by the flux of particles that return. What is the flux of particles that return? Let me write phi escape equal F2 U2 plus V squared divided to V. Well, the flux of particles that, okay, I clear all this now. The flux of particles that return to the shock will be the exact complement of this, meaning that the flux of particles that go back to the shock is now provided by the particles that satisfy the condition U2 plus V mu less than 0. Right? These are the ones that are moving leftwards. So this implies that mu must be less than minus U2 over V. And the probability is exactly the same, but now the integral extends from minus 1 and minus U2 divided by V. Okay? Now I'm not computing it again, but the thing is, it's exactly the same calculation, and the result is that this time you find F2 divided to V, U minus V squared. Exactly the same calculation. And, sorry, U2 minus V squared. So we can then compute P escape. P escape is going to be, as we said, escape flux divided returning flux, and this is equal to U2 plus V squared divided u2 minus v squared. So this is equal 1 plus u2 plus 2u2. u2 is, since v is the speed of light, now let me call v just the speed of light, okay? This I can write as 1 plus 2u2 divided 1 minus 2u2 over c, and this is 1 plus 4 u2 over c. There must be a minus, so something went wrong. So let me, okay, let me correct it this way. Probability of return is this, and which makes it much easier. E2 minus B. Okay, so this is minus plus. Does it make sense? And now I find that P is 1 minus 4 U2 over C. This is the probability of returning to the shock. And of course, then the escape probability is just, I don't know what I did wrong, but the escape probability is then 1 minus P return and the escape probability is just 4 U2 over C. Okay. Well, okay, now we're ready to input this information into this equation here. So we found the escape, and I can now write that n k plus 1. Well, let's leave it as it is. And now what we'll do is to compute k. Okay, so we will divide these two equations one by the other, and k divided n0 is going to be equal, so let me compute the following things, logarithm of, yeah, we need a break and I need a coffee. And k divided n0 is equal k 1 minus p escape times k logarithm of 1 minus p escape. Then I do the same on the equation on top, and I find that logarithm of ek divided E0 is equal k times the logarithm of 1 plus g. Okay? And then I can use the expression of k from this equation here into here, so that I can find sort of a spectrum, a relation between, and a relation for nk as a function of k. So I will substitute k here, let me rewrite it. Logarithm of nk over n0 is going to be equal to logarithm of ek divided E0, logarithm of 1 minus p escape, logarithm of 1 plus g. Okay? Okay, and now we have that nk over n0 is going to be equal ek over E0 to some power minus gamma, let me call it, with gamma equal to minus the logarithm of 1 minus p escape divided the logarithm of 1 plus g. And let's write what these are. So that is going to be logarithm of 4u2 divided by c divided the logarithm of 1 plus g, which is, where is g? Oh, here. So that's 1 plus 4/3 u1 minus u2 divided by c. And this is equal to, let me approximate the logarithm by its argument. This is going to be 4u2 divided by c, and this is 3c over 4 u2 minus u1. No, what did I do? Wait. Oh, yeah, sorry. This is 4u2 divided by c, 4u2. Okay, yes. And I'm left with the spectral index now, so-called spectral index gamma, which is equal to 3u2 divided u2 minus u1. And if I express u2 in terms of u1 and the compression ratio, I can divide everything by u2. This is 3 divided 1 minus r, with a minus in front. Because I was using gamma as minus, I lost the minus somewhere here. So this is minus, minus, and this becomes 3 over r minus 1. Okay? Now, this is the probability, so this is the spectral index that describes the number of particles with energy kappa. The spectrum is usually defined as dn dE, so I must divide by a power of E, and the power of E by which I divide gives me here a further plus 1, right? So the spectral index will be minus gamma minus 1, so this gamma plus 1. If I want to, let's call it gamma E, the particle spectral index in terms of energy. And so finally, I find that the particle spectral index is going to be R plus 2 divided R minus 1, which for R equal to 4 is 2. Which is the standard story for the Fermi accelerated spectrum. It leads to a particle distribution which, at a strong shock, has a spectrum e to the minus 2. Okay? We now stop here, and we take a break by what? 20 minutes? 15, what?
You decide, I mean, you have the...
Yeah, but, okay, time for a coffee. Let's say 15, 20 minutes, okay?
It's all yours.
I really need a coffee now.